Welcome back to CCNA 2. So let's go into some detail about some stateless automatic address configuration. So not every network has access to dedicated server hardware. Sometimes we may not want to run a DHCP server for some reason. So we can use SLAAC to have hosts automatically generate their own addresses without having to rely on a DHCP v6 server. So SLAAC really is just a service on the host. There's no server assigning or tracking or maintaining a list of addresses by use on one device or the other, like we're used to on IPv4. So SLAAC is going to send periodic router advertisement messages providing addressing and other configuration information to hosts to automatically configure those addresses. Now, the router advertisement messages will come from routers to your hosts to give them the prefix length, the global unicast routing prefix, and stuff like that. So our host, if we don't get one of those router advertisements, we can send a router solicitation to request one. And we'll send that to an all routers multicast address. So every router will subscribe to this multicast address, ff02::2. So you'll see here we enable IPv6, very, very important. Do not forget this command, write it down somewhere. Very important command right there. And we can show IPv6 interface and we'll see, hey, we have a global unicast address. We must have configured it up here, like maybe from the slides in the last section, we did that. And then you'll see link local address is also configured. I think this is addressing from the last section here. We've got a prefix length there, /64, and you'll see joined group addresses. These are our multicast, and F is F02::1 and FF02::2. That's our all routers multicast group. Now the FF02::1 is an IPv6 all devices group. So if you need to send something like a broadcast to all devices, technically not a broadcast, it's technically a multicast, but it's a multicast to every IPv6 device. FF02::1 is our multicast address for that. So if we're only using SLAAC, we will turn on our A bit, and that will say, hey, automatically configure your IP address, all the information you need. O and M are used, we have more information from a DHCP-v6 server, whether that's just additional information or addressing information. So other information here would be the O bit, and the M bit would be if we had to manage our IP addresses on our DHCP-v6 server. You'll see here, SLAAC only, we will end up with something looking like this. This is usually auto-generated from the MAC address. So we have this first 64 bits, which are per the router's interface and prefix. And then the remaining bits are going to be in the interface ID. So usually we'll actually take our MAC address and use it to automatically generate this. Now, Windows has adapted this and they've come up with a new way of randomly generating this because there were some security concerns over using your MAC address. Well, now by your IPv6 address, everybody knows the manufacturer of your device, and that could be kind of a concerning security vulnerability there. So and that's what I was just saying here. We have this randomly generated thing, which is now used by Windows 10, and then EUI64, which is using the 48-bit MAC address and inserting the hex value FFFE in the middle of the address. This is how you can tell if an IPv6 address is made with EUI64, is that FFFE. Now, some other operating systems will default to a randomly generated interface ID instead of the EUI64 due to privacy concerns, but it's either random or it's EUI64. We can also modify it in pretty much any OS to how we want to use it. If we have some different kind of rules we want to set. This is how the EUI64 process works. We take our information from our MAC address, we split it up into the OUI and the device identifier, right? and then we put FFFE in the middle, and we will actually flip this 7th bit here. So this bit has a value of 2. If you don't remember, we have 1, 2, 4, and 8 as our bit values, right? 1, 2, 4, 8. And so that 7th bit there from the left would be a value of 2. And so you'll see that we went from Charlie here to Echo. So we went from C to E, Charlie to Echo. That is 2 difference, right? There's a D in the middle, right? Hopefully you know your alphabet. So we went 2. Now, if it was the other way around, we would go 2 down instead of 2 up. So we may go from C to A if this was on. Now, of course, if this bit was on, we would have started with E and ended up with C, but, you know, it's a whole other story. Math and stuff. Hopefully you guys have a good grasp on that math there. If not, go back and review that binary math. I know you guys just love binary math and you're super excited to review it, but, you know, there you go. So, duplicate address detection, also known as DAD, will ensure that the IPv6 global unicast address is unique. We want to make sure we don't have conflicting IP addresses, just like an IPv4. So we'll send out a neighbor solicitation message, which basically says, hey, send to everybody, if you have this address, let me know. It's kind of like a ping. If no devices respond to that neighbor advertisement, then we know that it is unique and nobody else is using it. If it's received and the address is not unique, the host will then, if a response, a neighbor advertisement to that neighbor solicitation, right? The solicitation is a request, the advertisement is a response. If we get that and it's received, we generate a new ID and start all over again, right? We send it out to everybody and make sure that nobody's using it. Duplicate address detection is not really required because we have 18 quintillion possibilities, but we recommend that it's used. It's really not that bad. I would turn it on just to be on the safe side. I know we've used duplicate address detection on IPv4 in the past, but using it, especially when you have auto configuration, is very, very important. So that's it for SLAAC, or Stateless Automatic Address Configuration. I, for some reason, have trouble saying that. But join me in the next video and we'll go over DHCPv6. I'll see you then.